so this lesson is going to be over R.6, the rational exponents. So we're going to continue talking about the exponent rules. We talked about that earlier in the chapter and went over all the base ones. So if you need to review that video, that was R.3. The very first video was a list of all the exponent rules. So we're going to use some of those again here in R6. So the first one I want to start with is example 2. We've got a division with like bases. So the rule says if you have like bases, you subtract the exponents. So 5 minus 2 can be subtracted and make 12 to the third. Now it's questionable whether we need to reduce that further. We could work that out on our calculator or just leave it like that. So it depends on the directions. The next example, again, like bases. So I can work this and just bring over the A. Top, subtract the bottom is the division rule. So it'll be 5 subtract negative 8. So don't forget there's a subtract in it and there's a negative on the denominator. So it'll make a double negative, which will turn to a positive and be a to the 13th on that. Another way to do it, which I think is probably easier and find students make less mistakes, is when I see a negative exponent, we talked about a rule earlier that said any negative exponent can be moved to the other numerator denominator, just the reverse of where it's at, and it'll change its sign. So we also could have worked this, and I think this is a little easier to do, is pull that up to the top, it's a to the 8th, and then it'll be times on to a to the 5th, and then it's easier to do that work and say, like bases, you add the exponents to get to the same answer, right? A to the 13th. Okay, next example. Because these are multiplied, we're allowed to reduce this individual parts. It's not like that last section we did where we had plus and minus signs always make more complicated algebra. But here we're free to reduce the fraction part. The 16 and 12 can be reduced by 4 into each of those. And then do the like base IMs. My strategy I used on the last one, I would recommend bringing this m to the negative 9 down to the bottom, where it's m to the positive 9, and then adding your exponents to get m to the 20th on the bottom. So you have only a 4 left in the numerator, a 3, and an m to the 9th in the denominator. Oh, sorry, not just m to the 9th, but add my exponents and have m to the 20th, right? All right. Next example. And as always, I encourage you to pause the video to practice these as I'm going through them and try your work on your own before I complete it to see how we compare. So you can get some practice in. All right, the next example is similar to this last one. It has lots of parts, but these are monomials. There's little time signs between there, so we are free to just cancel away any common matching factors. So the 25 and 10 can be reduced just like all fractions can be reduced by dividing a common factor into each part. So 5 goes into each of those, 5 into 25, and 5 goes into 10. So reduce that fraction. Then R7 and R9, you would subtract 7 minus 9, which would be a negative 2, so it winds up going to the bottom. Or another way to think of it is you've got 7 R's and 9 R's, so whenever you divide out the common R's, you're going to have 2 R's left on the bottom. Z5 and Z to the first, don't forget if you don't see an exponent, it's 1, so 5 minus 1 will leave Z4 in the numerator. So what's left, you have a 5 on the top and a Z to the 4th. In the denominator, I have a 2 and an R squared, and that's how you'd leave your answer. All right, moving on to the next example. Example 3. So you can just keep on adding in lots of little exponents and all these rules jumbled together and make this more complicated. So this one looks kind of complicated, so I'm looking at it. What I would tell you is order of operation is an important detail here, that you need to know you cannot multiply these two together until you apply the exponents. You remember, please excuse my dear Aunt Sally, which says you do the parentheses first, then you do any exponents. So this parenthesis doesn't have anything really to do inside of it, I wouldn't say, but then next would be its exponents. Then you can multiply, which would be here, multiply and divide on the same level, and then any add and subtract is last. So that prevents us from multiplying this first. We have to do the squaring before the multiplying, just to remind you that. So 4 is squared. We can write that as just 4 squared or 16. If it's kind of a small number, we'll usually go ahead and work it. If it's a bigger number, kind of leave it. So I would go ahead and call that 16. So we had a rule that says a power to a power multiplies the exponents. So that's x to the negative 2. And then negative 5 times 2 is negative 10. So that applies that step. Then we are multiplying by 3x to the negative 2. And actually all of this would be considered a multiplication. There would be understood little time signs between every part of that. There's no plus minuses between the terms. So it's just one big term that needs to be multiplied. So 3 times 16, multiply like we always have. And then all these x's need to be worked on. And since they're multiplied, we add exponents when we multiply with like bases. These are all like bases. So negative 2 plus negative 2 plus negative 10 for a total of x to the negative 14th. And then, lastly, I cannot leave a negative exponent, so I'll move that down to the denominator. Yeah, the last form is we should never leave a negative sign in our final answer. We should always move it to the denominator or numerator, just the opposite place, to get rid of the negative sign on an exponent. All right, let's try that again. If you're following along in the book, I was sort of pausing because I wrote the problem wrong. So the answer that I had on the board was correct for the problem that I wrote, but I wrote it different than it was in the book. So that's if you were worried about that. Okay, so the next one, we have all these are times, so we're free to start moving things around and simplifying the parts that we can. So 12 and 8 can be reduced by 4. 4 into 8 is 2. 4 into 12 is 3. Then I can work on the p variables because they're like bases. You can apply your rules to it. What I recommend is I move this negative to the top and make it p to the positive 2. And then I've got p to the third times p to the second for a total of p to the 5th. So I have 3 and p to the 5th, again because that moved up. And that takes care of all that. And then for the q's, I would move this q to the negative 1 down below, which makes it q to the positive 1. It's multiplied by another q, so I'll add 1 and 1. So in the bottom, I'll have q squared, and also the 2 is sitting over there, don't forget it. And that would be your final form of that answer. All right, moving on. Another detail in this section is how to use a fractional exponent. So let me put a couple of examples of that. Again, all these were mentioned in our earlier section when we talked about exponents, so I'm just kind of hitting them again with a little harder examples you can see in R6. All right, so what does a fraction exponent mean? It means that's a radical. That can be rewritten as a radical problem. The 36 is what we call the radicand. The fraction exponent, the top represents the exponent on the radical, so it's to the first power, and the denominator represents its root. So this would really just be a square root. And when we do square roots, we usually don't show that 2, and we usually don't show that 1 when something's to the first power. So really, this could be just written as square root of 36. But anything to the 1/2 power is just another way of saying take the square root of it. So 36 is a perfect square, so we can find the root is 6. The square root is 6. On this next example, we've got the negative sign to worry about. When the negative sign is not in the parentheses, it is not part of this power. It is not understood to be raised to that power. If it were, it would have a parenthesis around that. So this is what I call a weighting negative. It's 100 is raised to the 1/2 power, which would be 10. And then the negative sign is like a -1 multiplier at the end you put on at the end. All right, next example. Let me move down a couple. Let's see. if it was written like this, with a parenthesis around the negative, that means you've got a negative raised to a 1/4 power. The negative is part of the root, or part of the radicand. You got to put it in there and apply this power to it. So we're trying to take a 4th root and then raise it to the 1st. So a 4th root of 1296. Well, you can't do a negative times a negative times a negative times a negative an even amount of times and work out to be a negative. You know, when it's an even root, like with square roots, if this would have been negative 100 to the 1/2, I could not have worked that. It wouldn't have been real. That would have meant the square root of negative 100, which is going to be an imaginary number, which we'll talk about later in the book. But there's nothing times itself. An even amount of multiplying with a negative always makes it positive. So that can't happen. It's imaginary. So we'll have a way of dealing with that. But for right now, it's just not real. And if you try it on your calculator, it's going to give you an error reading as well. So you might confirm that. So if we're doing an even root and it's a negative, it's not going to be real. Just not a real number. And for now, we just would not work that. One more example before I leave this idea. Let's do a different root, a 1/3 root. So a 1/3 root would be a cube root. Now we can do negatives that are odd rooted because an odd amount of negatives is doable. A negative times a negative times a negative is a negative. So that can be worked out. Negative 3 times negative 3 times negative 3 would equal negative 27. So that is a real answer. So a negative odd root can be worked, but a negative with an even root cannot, not in the reals. Let's look at example 5. Now, if there's a number on it, you can practice these on your calculator as well, and I always encourage you to practice on your calculator. They're all a little different, so it's good to practice with the calculator you're going to use throughout your semester. Be familiar with how that works. So these I want you to practice and use your exponent application, which is either your up arrow or your X, the Y button, depending on your calculator, and do this as a fraction and confirm that you're getting the same answer. But you will need to know how to work these by hand as well, because we'll do this with variables and then you won't be able to use your calculator. So you do need to understand the rule. So it's a cube root, and we're going to square it this time. So the cube root of 125 is 5. That is a perfect cube. And then we square that answer for an answer of 25. So again, do practice that on your calculator. Practice typing that in and see if you also get your 25. The next example, 32 is the radicand. We're doing a 5th root this time and raising it to the 7th. So the 5th root of 32, you might have to think about that one a bit, but it is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2, 5 times I did that, is 32. So 2 is the root, the 5th root of 32, and then we take it to the 7th. Again, because that's kind of large, it's kind of questionable. Do you work that out or not? So depending on the directions, you may or may not, but it is 128. One more example. This negative is my weighting negative, so it's not part of the discussion. It's like a negative 1 times onto, then do this stuff. So it's 81, it's a square root, and then we're going to cube it. So 81 is a perfect square, comes out to be 9. 9 to the 3rd then can be worked out. 9 to the 3rd, let me see what that is 729. And then lastly, after we finish our radical and our exponent stuff, then times it by the negative sign or the weighting negative will ultimately make that answer negative 729.